Hi, this is Brax, and this is my video for the LIDAR sensor. So the idea for the project is, you go to grab that pencil, it whisks away from you on that servo motor, and goes back when your hand goes away. Now I'll explain a little more in depth into how the project works. So the main component here is the LIDAR scanner, and how LIDAR works is it sends a light wave out one of these eyes, I'm not quite sure which, and it'll bounce off an object and return to the other one. So one emits and one senses, and then it calculates the distance of the object it bounced off of based on the time it took for it to bounce off the object and come back. Sorry, the thing is going back and forth because my hand is getting in the way. Now, how the LiDAR is set up with the Arduino is with these three cables. So this red cable here is power, and it's coming from 5 volts of power on the board, and this red is ground, or this black cable is ground, and it goes into ground on the board. And then this yellow is for the monitor and triggering of the sensor, which returns the data. So it comes over here where it branches, where it can go through this 1000 ohm resistor into this cable, or it can go straight into this yellow cable. So most of the time it goes through this yellow cable into this digital input, and it'll do this because the resistance is not great enough to also go through this resistor. However, when it takes a reading, the current coming out of this cable will be great enough to go through this resistor to overcome the 1000 ohms of resistance, so you'll receive data from both this black and yellow cable, which will be in these two inputs or outputs. And then I have the servo motor here, which is pretty simple. It's the same way I used in my last project. It has 3 cables going to the board. It's got black, which goes to ground, red, which brings 3.3 volts of power, and white, which is the data in which the board will communicate where to go to, and that white cable goes into a digital output on the board. Here's the schematic of my project alongside a drawing, both made on Tinkercad. And the first thing you'll notice is that this isn't actually a LiDAR sensor, this is an ultrasonic sensor, because Tinkercad doesn't have a LiDAR sensor in its library, but it measures distance. It has 2 eyes with a emitter and receiver, and it has 3 pins that are the same 3 that I used in the LiDAR, so it works for this purpose. You can see it has the same 3 pins of power, ground, and data, and the power is connected to 5 volts on the board, and the ground goes into ground here, and the data branches off into this branch here, which can go through the 1000 ohm resistor or right into the board, and it has the trigger and monitor pins like I explained earlier. And then here you got the servo, which has 3.3 volts of power from the board, ground, and the digital output. And here on the schematic, I think it actually did a really good job of the schematic. It's nice and simple. You can see it's the board here. It says Arduino Uno, but I'm actually using a Mega, but it uses all the same pins. It has everything that I need, so it works. You can see I got the sensor, which comes from 5 volts, has a ground into the board. It shares it with this in the schematic when it comes to the board, and the signal, which comes into this branch here, which corresponds to this branch here, where it can go through the resistor into a digital input on the board, or it can go straight into a different digital input on the board. Then you have the servo, which comes from 3.3 volts of power, the signal, which goes in digital output, and the ground. Here's the code for my project, written in C++ in the Arduino IDE. And I took a good chunk of the code from the GitHub link provided to me, or at least the part of the code that deals with interpreting a distance from the LiDAR sensor, because it's a bit tricky. So starting off here, I'm just including all the libraries I'll be using. This is for the LiDAR, this is for the servo, and these two were included with the GitHub code. There was a bit of extra code in there that I didn't need, which required these libraries, which I took out. I didn't bother to delete these libraries, so I don't use these two libraries here. And here I'm just defining a servo variable that I will be using. And here I am defining a LIDAR that I will be using. Then here I'm creating variables. It's different from how I usually do it, but that's how it was in the GitHub file, and it works, so there's no really need to change it. The monitor pin, which is 3, because I'll be using that to assign a digital input, which you'll see in a sec, and trigger pin, which I'll be using to define a digital output. Then I'm creating several variables called distance, start time, end time, new distance, and measuring. And you'll see how those come into play in a little bit. And to start off, I'm setting new distance and measuring both to false. And here in the setup loop, first I'm just initializing the serial monitor, and then I'm establishing the DIOs I'll be using as inputs or outputs. And here I'm establishing start time to micros. What micros is the amount of seconds since the program started. So this is changing constantly. Or I believe not seconds, sorry, the amount of microseconds since the program started. So it's changing constantly. And then end time is equal to start time for now. And then I'm just establishing that the servo motor is connected to pin 8. Now here is the part of the code that repeats. And for these first part is obtaining a distance from the LiDAR, and then just this little loop here is the part that actually controls the servo motor. So I'll go over this first part first, and then I'll just add on this part later, and you'll see how they connect. So starting off, if digital read monitor pin, that means if there's a reading from the monitor pin, it sends us into this loop, which is if measuring equals false. And measuring up here is set to false by default, so it'll initially go into here. And it sets start time to this micros variable, so it establishes a point in time where it starts measuring. It says measuring to true, so we know that it's measuring. And then it had measuring been true, we'd go into here, and I'll enter here. I'll simulate how the code is going through this. So I'll enter here once we come back in this loop. But for right now, we're skipping over this because my measuring is equal to false, and we're bumped out of this else. And now if new distance equals true, which is not true, because here it's set to false, we'd go into here. But we're not, so we're going to skip here, and I'm going to skip this part for now, and we get bumped to the beginning of the void loop. So now that measuring and new distance are equal to true, we get sent into this loop, which if measuring equals true, end time equals micros. So it's a different micros number because it's constantly changing. So now we have 2 points of time. We have start time and end time. And measuring equals false, so we turn the measuring off so we don't get sent in this loop. Next time we come around, and new distance equals true. So we have a new distance, which is this difference in time. And then you'll see that comes into play here with if new distance equals true. So if there's that difference in time, the distance equals the end time minus the start time, which is the elapsed time between the end and start, divided by 10, which is the conversion to centimeters of distance the LiDAR gives. And then, so that's how we get the distance. And then we're just printing that to the serial monitor and delaying a little bit so we can read from the serial monitor. Then new distance equals false, so then we don't get bumped into this next time unless we have new distance. And there's this little if loop here, which I mentioned earlier, which is where the servo comes into play. If the distance is less than 30, servo write 20, which means if there's an object less than 30 centimeters from the LiDAR, turn the servo to 20 degrees, and if not, so if there's nothing within 30 centimeters, write 110 degrees, which is the upright position. So basically, if there's something within 30 degrees, it'll lie flat, and if there's not, it'll go upright, which you see with my hand comes close, the pencil goes down, and then when it leaves, it goes back up. Here you'll be able to see the serial monitor printouts of the distance alongside the project with my hand grabbing the pencil. So you can see right now it's returning a distance of about 260 to 270 centimeters, and that's just bouncing off the wall on the other end of my room. But when I put my hand here, you see the distance goes down to 17 to 18 centimeters, and the pencil goes back, it's less than 30. And bring my hand away, the distance jumps back up to above 30, and the pencil goes back. Right, if I try and grab it, right when it crosses 30, it'll go back, and right then it's right because my fingers are kind of under the thing, so I guess it doesn't really do its job very well. If I bring it back up, it'll go back because the distance is less than 30.